Okay, so in this video, we'll be talking about linear regression. Now, we won't be focusing on the rather traditional stuff that you might already be knowing, but instead, we'll focus on the geometrical meaning behind what correlation is. Now, it's not just any geometry behind correlation video that you'll find on this platform, wherein I'll tell you that linear regression is nothing but a best fit line for a set of points on a plane, but rather this video focuses on the why of geometry um, rather than the what of geometry. And by that I mean we'll be dissecting the formula of OLS and we'll try to understand why does this formula work? Why does it give you the slope of the best fit line? So we'll be dissecting the OLS method for estimating the linear regression parameters. And by the way, the things about geometry that I've told you before, those are actually the prerequisites for this video. I want you to know those things before you move on to this discussion and get involved. Okay, so enough of talk and let's write the topic of discussion, which is linear regression. Rather, regression. Let's recap some of the basics and build up the foundation from the very scratch. Regression. There are, I'm sorry, there are actually two types of regression mainly. The first is called the linear regression, and the second is called the multiple regression. And there are two ways for estimation. There are two ways for parameter estimations in linear regression. So parameter estimation in linear regression is, let me write that first. Estimation in linear regression and in multiple regression are done in two ways. The first is an iterative process. Which is also so iterative processes are done using optimization algorithms. Optimization algorithms like gradient descent or gradient ascent, wherein you optimize your model with respect to certain functions. Like with respect to loss, you provide the minimization gradient descent to minimize the loss in your model. Or there's also gradient ascent functions, gradient ascent optimization algorithms, which actually maximizes certain functions to estimate your regression parameters. And the gradient descent algorithm uses functions like maybe log likelihood, wherein you have to maximize that function in order to get to the best fit line, in order to estimate the best fit line. So the first method of parameter estimation is actually using optimization algorithm. Now the second method is using the mathematical formulae, and here comes our OLS, and OLS stands for ordinary least square. Here we use mathematical formula to estimate the best fit line, the parameters of the best fit line. It's actually a very manual process kind of, but the optimization algorithm, it's an iterative process. We won't be discussing about the optimization algorithm or the iterative processes for parameter estimation. Instead, we'll be focusing on the OLS part. Now, let me give you a brief segmentation of this particular discussion. The first thing that we'll discuss is the rotation of best fit line about a point. And the second thing that we'll discuss, which I think is the juice of this discussion, um, is the analysis and geometrical interpretation of OLS. Okay, so let's move on to the first segment of our discussion: rotation of the best fit line about a point. Now, this part actually involves some differentiation, some knowledge of calculus. If you have um, if you have studied calculus in your high school, this requires very basic knowledge of calculus. You don't need to be um, a mathematician to go through this particular segment, the first segment. But yeah, you do need some basic knowledge, some basic differentiation about some basic knowledge about differentiation. I'm sorry, to get through. So rotation of the line about a point, rotation of the best fit line about a point. So this is our first discussion, the first point of discussion. Before that, let me tell you how linear regression, um, is written. I mean, what is how do we actually represent linear regression mathematically? So there are multiple ways, but this is one of the ways. Y hat is equals to beta naught hat plus beta 1 hat x, right? And the second way is h of theta, I'm sorry, h of x theta is equals to theta naught plus theta 1 x. This is the slope parameter of the line. If you have studied straight lines, then you might recall that this is how we actually write the straight line equation as well. Y is equals to mx plus c. This is called the slope point. I'm sorry, it's the slope intercept form. Yeah, yes, it's a slope intercept form. Slope intercept form of the straight line, of a straight line, right? There are many ways straight lines can be represented as well. Okay, so theta 1 parameter and beta 1, it represents slope, and beta naught and theta naught, they are constants, the intercept. Now, so to perform linear regression, these are the parameters that we need to estimate: beta 1, beta naught, or theta 1, theta naught. Okay, so when I say rotation of the best fit line about a point, then what I actually mean is there is a point on your data set about which the best fit line rotates. So to find its best orientation, kind of. See, you need 2 points to uniquely identify a straight line, and what I'm trying to imply when I say rotation of the best fit line about a point, then what I'm trying to say is there is a fixed point on your plane about which the linear regression line has to pass through. That and while passing through that point, it tries to find the best orientation such that the RSS is minimized, the residual sum of squares is minimized. If you don't know what RSS is, then RSS is the amount of error in your data set squared. Residuals is nothing but, residual is nothing but y minus y hat. That's it. So the amount of error that you have, this is, if this is your real point, um, true point, and this is your estimation, then this is the error. I'm sorry. Yeah, this is the error. This is y. This is y hat. This length is the amount of error that you have in your model. Error or residual. It's a regression specific term, residual. Now, because the because this value can be positive or negative, that's why what we essentially do is we square this value so that so that so that the negativity kind of, so the negativity of the expression, um, so that we can nullify the negativity of the expression, and the value always remains positive, whether the point is lying up or down. And when we square all of these errors and sum them up for all of the points, so say we have these points as well in our data set, and we have calculated the errors for all of those points and we have summed them up, then that expression is called the RSS. And RSS is equals to summation wherein I goes from 1 to n, y minus y bar squared. So again, coming back to the topic, what I'm trying to say is there's a fixed point in your plane about which the best fit line has to pass through, and it will orient itself such that the RSS is minimized. Okay, now what is that point? Well, the point is actually very easy to find out, but first let's make a kind of a proxy data set for our discussion. Okay, so let's say these are our data points. Okay, and now let's move on to finding that point. Now to find that point, what I will do is so we know that this particular function has to be minimized in order to find the best fit line, right? Now, if you have studied minima maxima in your calculus classes, then you know we need to differentiate a function and equate it to zero, because I don't think we should discuss this, but still let's recap. If you're not able to recall, then let's recap that thing, that particular concept as well. That if, let's say, this is a function, then at the points of maxima and minima, the slope is actually zero. The derivative of the function is actually zero. Now, as this particular function is a quadratic function, you'll get a parabola, right? So when you'll differentiate this function, then and equate it to zero, you'll get to this minima point, right, where the derivative is equal to zero. Okay, let's go and differentiate this function. So we have to find the minima, RSS min, for this particular expression. Okay, so I is equals to 1 from I equals 1 to n, y minus. Now what I'll do is I'll substitute the value of y hat from this expression, from the first expression that we have, into this function. So we'll have beta naught hat minus beta 1 hat x squared, right? That right now I have not differentiated the Right now I have not differentiated the function, and now if I'll differentiate the function and apply the power and the chain rules, oh, I'm sorry, yeah, now if I'll differentiate the function and apply the power and chain rule, then what you will get, let me make some space in here. Yeah, now if you apply the power and chain rule, what you'll get after differentiation is something like this. So I have differentiated this function with respect to beta naught. Okay. um, I have not differentiated this function with respect to x. I have differentiated this function with respect to beta naught. So the two, after applying the power, the two come out of the summation mark, and we'll get beta 1x times minus 1. Then if you apply the chain rule, so this the differentiation will be done in the chain rule. First we'll apply the power rule, and then we'll move into the function and differentiate by parts. Okay, so and let me equate it to 0, so to find the minima. Okay, now we will bring 2 on the other side and will get cancelled out, and what you'll be left with is summation I is equals to 1, and I've multiplied this minus 1 into to this equation. So what I'll get is summation, these two will turn positive and this will turn negative, right? So beta naught plus summation I equals 1, I equals 1 to n. Beta 1 is obviously a constant, so it will come out. Okay, let's move on with it. Plus what is left? Okay, we'll leave this minus. Okay, this is what we'll get, right? Now if this is a constant, therefore summation of a constant is just n times that constant. So n times beta naught plus here beta naught will come, beta 1 will come out of this this summation mark because it's a constant. These are the properties of summation. Summation symbol, summation mark, x minus I equals 1 to n y. Now let's now what we'll do is we will separate this beta naught from the rest. So we'll bring beta naught to one side of the equation, the all the other variables onto the other side. So it will become beta naught is equals to summation I equals 1 to n y 1 upon n. So this n, the n was actually multiplied over here. It will come to the denominator on the other side, minus beta 1 hat. I've actually forgotten to put the hat over there as well. So beta 1 hat summation x I equals 1 to n divided by n. Now the summation of all the the summation of all the points in your dependent data set divided by the number of points, summation of all the points in the independent data set divided by the number of points, it will give you average, right? So y bar minus beta 1 x bar. Now if you'll observe, let me write it another way so that it's more visible than it's more visible to you to observe what I'm trying to make you observe. So y bar is equals to beta 1 hat x bar plus beta naught, or maybe like this. No, I think it's I think that'll do the work. Now let me write in another color. Y bar is equals to beta 1 hat x bar plus beta naught. Now we get the, so how do we got this result? So we got this result after differentiation of the function with respect to beta naught, and this function, so this value is true by definition, and by that I mean that the original equation looked like this: y hat is equals to beta 1 hat x plus beta naught, and this particular equation tells you that if for whatever value of beta naught and beta 1 that you get, this condition will always be true, and the condition it is specifying here is it will always pass through the point x bar and y bar. This particular condition, this particular equation will always be satisfied no matter what the beta values you put in. No matter what the values of beta naught and beta 1 you put in, this equation will always be satisfied. So in English, so this is written in mathematical form. In English, what I'm trying to say is when you tried to minimize the RSS, then this condition kind of popped out of the equation, and it says that if you want to find the best fit line, if you are willing to if you're willing to find if you're willing to find the best fit line, or if you're trying to minimize RSS, then that best fit line should and must pass through the point x bar and y bar. This is the condition that popped out when you kind of differentiated your function, your RSS. So this is the point I was talking about. So x bar, okay, so we are actually heading towards the end of the first part of our discussion, wherein what I want you to take note of is the point x bar y bar is a point about which our best fit line kind of orients. And by that I mean, let's actually go to the plane that we had made earlier, and assume this and let's pick another color first, and assume this point to be x bar and this point to be y bar. Okay, so this point x bar y bar is the point about which the best fit line kind of rotates in such a way that to minimize the RSS. This is the point. This is the condition that popped out when we differentiated, right? So the mathematics is literally saying that if you want the best fit line, if you want to minimize the RSS, if you want to minimize the residuals, if you want to minimize the errors, then the best fit line must pass through this point, x bar, y bar. So let's say this is the initial line that we chose, which is not the best fit. So it will rotate about this point only. It will rotate about x bar, y bar only. And let's say we get this line. Maybe it's not the best fit either. So maybe it will rotate like this. And finally, we might get our best fit line to be coming out like that. Maybe. Just assume it to be passing through x bar, y bar. So this is the point about which you can say that our best fit line rotates. So even before starting any linear regression problem, you know that there is a point about which the linear regression line has to pass through. Now, if you have studied straight lines, then you might be knowing that there are 2 points. 2 points are actually needed to uniquely identify a straight line. Now, if you have got 1 point, then there's only 1 point needed further to uniquely to actually find your best fit line. So there's only 1 point needed more. You just have to find 1 more point, and after which your straight line will be fixed. And if I recall that property again, straight line. So what the property of straight lines is, there's actually only a single straight line that can pass through 2 points, right? There's only a single straight line which can pass through 2 points if their points are not coinciding, obviously. If the points are not coinciding, then there is only one and only one line that can pass through two non-coinciding points. Okay, so which implies that if you have 2 points, then the straight line is fixed. So one point is fixed for us, and in such cases, we say that the line is kind of rotating about this point to get to the line, which is the best fit. This is actually, this is how I say it, that the line is rotating about that point to get to the best fit line. Okay, so it might rotate like so. It might go through here, maybe. I'm so sorry for this. This is the last attempt that I'm making. Yeah, maybe after this it rotates like this. So, and after this rotation, it finally reaches the best fit line. This is the point of rotation of the best fit line, the point x bar y bar. And here, our first segment of our discussion has been ended. Now, so 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 I don't want to actually make this video longer now, because 28 minutes approximately have already been passed, and we have only completed the first segment of our discussion. So let's move the second part to another video, and we'll actually discuss the second part in the next video, where we'll actually get the juice of this perspective lesson, that is dissection of the OLS formula for finding the slope of the best fit line, for finding the beta 1 parameter. Now, as you can see, beta naught can easily be found out by this formula, y bar minus beta 1 hat times x bar. But to find beta 1, we'll have to apply another formula, which is called this which is called the OLS formula for slope estimation, and that we'll discuss in the next video. So please watch the follow-up video to get the real juice of this discussion. I'll see you in the next one.